Okay, so previously we had a lot of fun with intersection theory mod 2. But as fun as it is, it's not nuanced enough. It's a bit too crude. So we want to find an alternative. And that's why we're going to look at oriented intersection theory. Now let's quickly review the motivation. Remember, originally our tentative definition of intersection number is as follows. If we have a map F from a manifold M to a manifold N, and then Z is a submanifold of N that is transversal to F, then we tentatively define the intersection number between F and Z to just be the number of points in the preimage of Z. For example, in this picture, I'm drawing M as this top here, and Z are the yellow stuff here. F map this top to this space here. And so the preimage of Z under this F0 are just these points here. Thus, the intersection number of Z with F0 is just 4. And then we say that if a map G is not transversal to Z, then we can just deform G to a map that is transversal to Z, and then take the intersection number of that map with Z to be the definition of the intersection number of G with Z. The issue then is, what if there are two different maps that are both homotopic to G and transversal to Z? This is well defined if and only if the intersection number of two such maps are gonna be the same. In particular, we need homotopic maps to have the same intersection number. Intersection number has to be a homotopy invariant. And the problem is that this definition does not give a homotopy invariant. For example, in this picture, F0 and F1 are homotopic. Here, this is a copy of M and this is another copy of M. And we have a homotopy here, big F here, sending this whole product right into N. But observe here that the intersection number of F0 with Z is 4, right, corresponding to these 4 points here, whereas the intersection number of F1 with Z is just 2. So they are not equal. Previously, we resolved this by only looking at intersection number modulo 2, because the difference between this intersection number and this intersection number will always be an even number, because it's always going to be the boundary of some one manifold. However, there is another way to resolve this issue, which is to count point of intersection with orientation. So in particular, if this point is counted as 1, then this will be counted as -1. So these kind of bad configuration cancel out. They don't contribute anything into the intersection number. And in that case, then this intersection number of F0 and F1 are going to be equal. This motivates us to look at oriented intersection theory. For that, we need to first discuss what an orientation is. In this video, we are gonna just give a rough idea of orientation. Later, when we talk about integration, we're gonna dive deeper. We're gonna talk about how to think of orientation in terms of differential form and atlases and so on. We'll start by defining an orientation on a vector space, and then for a manifold, we'll define a pointwise orientation to just be the choice of orientation on each tangent space. So for each tangent space, we'll choose an orientation, but in a way that is compatible, whatever that means. Alright, so let's figure out a good definition for orientation on vector space. Let's look at the plane. Right, let's look at the vector space R2. Now on R2, we usually talk about two types of orientation. We have the counterclockwise orientation and the clockwise orientation. This suggests one way of thinking about orientation. Maybe we can think of orientation as ordered basis. For example, let's say V and W form a basis of R2, as drawn in this picture. Then these two ordering of V and W gives two different bases. So in this ordered basis, V comes before W, so we can think of this as the clockwise rotation, right? We go first from V and then W. And in this second ordered basis, W comes first, so we go from W to V, so we can think of this as corresponding to the counterclockwise orientation. That is a good start, but there is some issue here. For example, let's look at another ordered basis as drawn in this picture, this AB. Even though this is a different ordered basis, intuitively this should correspond to the same orientation as V, W, because this should also describe the clockwise orientation. So we should instead think of orientation as equivalence classes of ordered bases. These two ordered bases should somehow be treated as equivalent. So how do we define this equivalence relation? Intuitively, we can see that this should be equivalent, but how do we capture that formally? Well, so let me just define the equivalence formula first, and then we'll give some intuition for this formula. Right, so we'll say that this order basis is equivalent to this order basis if the change of basis matrix has positive determinant. And here, remember, the change of basis matrix is the linear transformation that sends V to A and W to B. And we say that these two ordered bases are equivalent if their change of basis matrix has positive determinant. For some intuition, let's just look at the case when these angles are the same, right? Then we can obtain these vectors from these by just a rotation and then some scaling, but scaling in with a positive scalar. And rotation has positive determinant. It actually has determinant 1, right? And scaling, positive scaling, also has positive determinant. So the transformation that sends V and W to A and B, being a composition of rotation and positive scaling, must have positive determinant. In the general case, we'll need to argue a bit more, but let's not worry about that right now. For now, let us just agree on the following definition. So on a general vector space V, an orientation is an equivalence class of ordered bases, where two ordered bases are equivalent if the determinant of the change of basis matrix between them is positive. Then we say a pointwise orientation for a general manifold M is a choice for each tangent space, right? For each tangent space, we choose an orientation in a way that is compatible. We'll explain what compatible means later. Next up, we want to talk about some induced orientation. The orientation induced on a boundary of a manifold, on products of manifolds, and so on.